questions 19 and 20 from that assignment, we're looking like this. And I think everybody got the same question. So it says triangle BCD has vertices at 8, 2, 11, 3, and 2, 6. Okay? And it asks you to prove the following information. It says type answer with a radical. It says you do not need to simplify. But they want to find, when it says BC, remember that's notation for finding length of BC. BD, length of BD, and CD is length of CD. So we know that our length should be found using the distance formula, which is distance equal to x2 minus x1 squared plus then y2 minus y1 squared, right? Now, if I'm doing BC, okay, the way I like to do this is I take the 2 points B and C, I put them on top of each other, 8, 2 and 11, 3. And now I'm going to do the distance formula with those. So I'm terrible at organization in regards to my work. When I do my work, it's it's all in the same kind of area on the paper, but it's not really easy to go back and follow my steps. And I know that I have that issue. So what I do a lot of times is I make sure that I label things correctly. So if things are kind of in disarray, I can at least know what the numbers that I've created represent. Is that going to make sense? If I just do this without putting notation, I do a distance and I get a number, and then I go do a distance for BD and I get a number, and then I get a distance for DC or CD and I get a number, and I didn't label anything, I don't remember looking at just that number right there. I don't remember which segment that came from. Does that make sense? But if I label things, it's so much easier to read my work. And hopefully you guys are starting to learn those types of things about yourself. Are you really organized? If not, maybe where can you make up that organization in another thing that you're good at? Okay? Are you detailed? Do you pay close attention to detail, like kind of labeling and stuff like that? That might help you organize a little bit better or compensate for your lack of organization. When I do BC, find that distance, I'm going to subtract my x's. So it gives me 3 when I do that, right? When you square that, you get 9. Okay, so that 9 is this stuff right here, x squared, or x2 minus x1 squared. Then I'm going to subtract my y's, and my y's are 3 and 2, right? So it gives me a 1 when I subtract them. Square that, and I get 1. So I get radical 10. Okay? And that's what they're asking you to put in this box here for BC, square root of 10. Okay? Now, as I was going through this, I just always use the distance formula. I always subtract an order. It gives me a positive number. It doesn't really matter because I'm going to square that anyways. Okay? So it's always going to force whatever, and we've talked about this many a times, but whatever this number here is, I don't care whether it's positive or negative, because then when I square it, that whole thing's going to be a positive number, right? And then likewise, this whole thing is going to be a positive number. Okay. The next thing I want to do is the same exact process, but do it with B to D. Okay, so B is 8, 2, and D is 2, 6. So subtract those x's, gives me 6. Square that, get 36. Subtract these subtract these y's, give yourself 4. Square that, you get 16, right? So that gives me radical 52 for that distance. Over here, radical 52. And now my last part is to find the distance of C to D. And the distance between C to D is now looking at what? C is 11, 3, and D is 2, 6. So subtract those two numbers. Gives me 9. Square that, gives you 81, right? Then add to that these two numbers subtracted gives you 3. Square that, you get 9. So I get radical 90. Okay. Now, the reason I didn't have you simplify those is because those numbers are really easy to compare. Even if you have absolutely no understanding of what radicals do, you should still be able to say how 10 compares to 52 and how then both those compare to 90, right? You can look at that and say which one's bigger. You can tell that, since all those numbers, those radians are different, those distances all have to be different. We talked about this in the last class, or one of the classes today. I said, if I know nothing about the multiplication, when you're in third grade or whatever, when you start multiplying, if I know 18 and 48, and I know 18 is smaller than 48, right? And if I multiply that, even if I have no idea what multiplication means, if I put a 5 there and then I multiply this thing by the same 5, do I know which product should still be bigger? Because I knew that 48 was bigger than 18, right? Even though I know nothing about multiplication. So it's the same idea with radicals. If I don't know that radical 10 is a symbol for another number, that when I multiply that other number together 2 times, I get 10. I can still make a distinction that these things are not equal. I can make a distinction of which one's bigger and which one's smaller. Okay? The one thing, if you do simplify them, because the end of course exams probably ask you to simplify them. If I do simplify them, we're looking for perfect squares that divide into those. 10 doesn't have any perfect square that divides it, but 52 does. Okay? When I see 52, and I don't play cards a lot, but I see 52, there's 52 cards in the deck, right? I know there's 4 suits in the deck. So I always see, when I see 52, I see 4 times 13. Okay? 4 is perfect square, right? So this actually reduces to 2 radical 13. Okay? And in 90, I see the 9 in there, right? 9 will divide 90. And this goes to 3 radical 10. And that is radical 10. Okay? Now, if I ask you to put those on a number line, it might be hard for you to realize where they go in comparison to one another. But if I ask you to put radical 10, radical 52, and radical 90 on the number line, you should be able to put them in the correct order, because you know how 10, 52, and 90 go on the number line. Does that make sense, everybody? So, as we're doing these coordinate proofs, it's a good idea in regards to finding distances to leave them unsimplified. Leave them unsimplified. Okay, because it's just going to make an easier comparison. All right. So when we do that, okay, the reason we're doing all this work is because we're trying to collect data about our triangle. We just figure out that our triangle has no sides congruent, right? Well, if it has no sides congruent, what would be my option down here that I choose? Scalene. Okay. That's what that distance, doing those distance formulas is going to tell me. If for any reason, maybe I got 2 of these distances to be the same. What if they're both radical 52? Okay, BC was radical 52, and BD was radical 52. I would come down here and choose isosceles, right? Okay. Now, there are some options here. How do I know to choose maybe if isosceles or right isosceles? Okay. Maybe I have a right scalene triangle. Okay, maybe that's an option. I don't know if I've got an option F down here. I kind of cut and pasted that kind of poorly. But I would want to know if I can better classify it with the idea of being right. Okay. Well, if it's going to be a right, it's going to have what type of angles in it? A right angle. Okay. So when we talk about right angles, okay, and just kind of help you realize this connection, and this is what I tried to do yesterday, but with the updated version, and won't let me do it very well. If I go ahead and I put that line in there, okay, actually that's a terrible line. Let's go, because the slope was 1. I want to use a slope that's not 1. If I look at that line there, okay, and I put it in y equals mx plus b form, and let me change the rounding a little bit here so you can see a little bit more of that slope. You visualize that that slope is 1/3. Okay, now it's cutting off because of the rounding ability of GeoGebra, but that's 0.333333 repeating. If I go to my rounding and ask it to do 15, you're going to see 15 threes. Okay, so that's verification that that thing's going to keep doing that pattern. So that's 1/3. Now, if I take a line that is perpendicular to it, so let's say I take that line right there, or any one of these infinite number lines I could choose, and I ask it to look at that equation. This slope here was 1/3, right? This slope is 3/1, right? Does that make sense? That's negative, and we'll talk about that in a moment. But this is 1/3, and this is 3/1. What types of numbers in comparison to one another are 1/3 and 3/1? How do we categorize those or identify them, define them? They're reciprocals. Good. Okay. So if the lines are going to be perpendicular, they have to be reciprocals. but one of those is positive, one's negative, right? Okay. And think about this. The slope of this line F here is going from the lower left to the upper right, so it's a positive slope. Well, you can't have anything that is perpendicular to that is also a positive slope. It's just not going to work out. Okay, geometrically it doesn't make sense. So you have to have a line that's coming from the left. Okay, from left to right, it's going down. Okay, so that's why they got to have opposite slopes. Okay, so we're looking for opposite sign reciprocals when we deal with perpendicular lines. And I can move this around and, oh, I thought I could. Can I? There we go. I can move that around, and I get the infinite number of different perpendicular lines, right? But look at that slope of G. Does it ever change from -3? No, because that line is always perpendicular to the other line, okay? And I can start moving things around. I can move A around a little bit. Let's say that I look at that, okay? Now, this is 0.666666 repeating. So that would be, what, 2/3? Flip 2/3, you get 3/2, don't you? Was it 3/2, 1.5? And we see then again that these are perpendicular, and we see that idea of slope being opposite sign reciprocals. So when we get to actually working on this problem, that's why they're asking me for these slopes. Okay. In general, and we'll talk about this here in a little bit, but in general, I really only need to look at 2 slopes. Okay. But I guess I don't want to say that. If I know that I've got a isosceles triangle or an equilateral triangle or something like that, I can minimize the amount of slopes I have to look at. For instance, if I have an equilateral triangle, if I found out BC, BD, and CD were all the same, would I have to look at any slopes to determine if I have perpendicular lines? No. What are all the angle measurements in an equilateral triangle? 60. So there's no way they could be 90, right? Okay. If I have an isosceles triangle, think about this. Let's see if I've got this picture still up here. If I look at this picture here, that's isosceles. Okay. Is there any way that angle A could be 90 degrees? Because if this is isosceles, angle A and angle C, how do they have to relate to one another? They have to be equal. Well, can this one be 90 and that one be 90? Don't we violate the 180-degree rule? Yeah. So, in the event knowing that I have an isosceles triangle, to save a little bit of work, I would only need to worry about this angle up here being a right angle. Therefore I only need to worry about segment AB slope and segment BC slope. Okay? So knowing the features of isosceles or equilateral or scalene might simplify some of my work. Now, because this is scalene, it's probably a good idea to find all 3 slopes. Okay? If you couldn't follow that, doesn't make sense to you, find all 3 slopes. Okay? Hopefully slope's not a bad calculation for us. It's not that hard. Okay? If you remember slope formula from last year, should be one of the main topics you took away from that course last year. It's y2 minus y1 over x2 minus x1, right? Okay. Now, all you've got to do is find the slope of BC. So slope of BC, I use subscripts to remind myself what that slope is referring to. But I'm going to look at B and C. Okay, so it says subtract your y's. So I'm going to go 3 minus 2. And then I'm going to subtract my x's. So I go 11 minus 8. Do that work, I get 1/3, right? Then I'm going to do the slope of BD. So B and D are those two. Again, it doesn't matter the order that you subtract the y's. I can go 2 minus 6 or 6 minus 2. Does that make sense? But how you decided to subtract those is how you have to then subtract your x's. So if I go 6 minus 2, 6 minus 2, so I went from this one to that one, right? So then when I subtract the x's, I got to start at the same point. I go 2 minus 8. Okay, these two things, your first term in your numerator, your first term in the denominator, have to come from the same ordered pair. The last term has to come from the same ordered pair. So now 6 minus 2 is what, 4? 2 minus 8 is negative 6. I'm going to reduce that, and I should get, what, negative 2/3? So there's that slope. And then we can do the one other slope CD. And we get, looking at those, subtract your y's. So I'll go 6 minus 3. And then I'll subtract my x's. 2 minus 11. So here I get, what, 3 again. And then 2 minus 11 is going to be negative 9. So now I get negative 1/3. Okay. Now as I look at those, there's 3 things, and I want to talk about determining whether I've got a right angle anywhere. And angles are created by 2 segments, right, in a triangle. So I'm going to pair up just groupings of 2 here. So I'm going to look at segment BC and BD. So I look at BC. There's quicker ways of doing this, but kind of breaking down logically. I'm going to look at this slope and that slope. So it would tell me where BC and BD come together. Think about it this way. Where would BC and BD, I don't have the picture drawn, but where would they be coming together? Where would they meet? At what point? If I look at BC and BD, those 2 segments are going to share what point? B, right? Okay. So when I'm looking at this, I'm actually trying to determine, is there a right angle at B? And because those 2 slopes, are those opposite sign reciprocals? No. Okay? So they're not opposite sign reciprocals, so they're not perpendicular, so you do not have a right angle at B. The next thing I want to do is compare maybe those 2. Okay? So where are those 2 going to meet? At what vertex? C. So I'm checking to see if there's a right angle at C. I've got 1/3 and negative 1/3, right? Opposite signs, right? Are they reciprocals though? No. So no right angle at C. And then the last comparison we've got to make is BD and CD. So that's checking angle D. And now we see that those are not opposite sign reciprocals either. So are there any right angles? No. So we have no right angles. We have no congruent sides. So the best way of identifying this triangle right now is just a scalene triangle. Okay? We can do a little bit of work later on to determine, is this isosceles or not? Sorry, not isosceles. Acute or obtuse. Okay. Once we learn some stuff about sine, cosine, tangent, law of sines, law of cosines, that stuff, which is like chapter 7 and 8. Now the reason I had you guys download GeoGebra is because my hopes are that understanding this is a pretty elaborate question, right? A lot of work there. Okay. My hopes are you do that work on a piece of paper. All right. Then you open GeoGebra, and you can quickly kind of reconfirm all of your thoughts that you had algebraically. Okay. So we had. Let me do it this way. Come on. We had points 8, 2. So I'm going to call B. If you remember doing this yesterday, I say B equals, and then parenthesis 8, 2. And then C equals 11, 3. And then D equals 2, 6, right? That's kind of what we did yesterday. The next thing we went through, and I'm going to readjust things so I can see it, so I zoom out a little bit so I can see it. That's our triangle, okay? Or I guess the vertices of our triangle. The next thing we did is we took our line tool, click on that, and it broke it down to segments. Okay, so I come down to segment, choose that. And then we just clicked from, B to D, and it gave me that segment, right? And I can keep doing that to find, B to C or C to D. I like to do it this way. If I just come over here and click C to D, it creates that segment. If I click B and C, it creates that segment. Okay. Now, here's the thing. This is why I think maybe GeoGebra is useful. This is maybe why doing things by hand is useful in the intercourse exam. When you guys are on the intercourse exam and they ask you, hey, here are 3 ordered pairs, determine what type of triangle this is, or maybe we're working with quadrilaterals or some other type of shape, and they ask you to do this work with it. If I draw that, because they're not going to give you graph paper, but they give you like 3 pieces of paper, 3 pieces of computer paper is what you're allowed to use. Okay, and you're going to have to maybe sketch this to organize your thoughts on your own. If you were to sketch this, you might write this or draw this just because of human error to where angle B might potentially look like a right angle to you, right? And you might accidentally classify it as a right angle without proof of it, okay? The algebra, the slopes, give us the proof that that is not a right angle, okay? But this is kind of what GeoGebra is going to do for us. We can go through and say, okay, what are the distances of these segments? So I'm going to click on this angle here, okay? And that brings up my measurement column, really. I'm going to go down to distance. Click that. And then I can just click on any one of these segments, and it's going to pop up those distances for me. Okay? And we see that they're all different, right? And they're all different, meaning to us that that's scalene. You could have also seen those numbers over here. Okay? But what we did it by hand, and we found radicals, right? Okay? Now, yesterday, the GeoGebra we downloaded yesterday had that keyboard down at the bottom, which was nice. There is a keyboard on this one, but it's hidden. I'll show it to you in a little bit. But if I just want to figure out if I've done the algebra right, we said the square root of, I think it was it BD? I'm sorry, BC was radical 10. BC was radical 10. So I'm going to type in square root of 10. And I get 3.16. I come over to BC. Was that 3.16? Okay, so I know radical 10 was done correctly by hand. BD, we said, was radical 52. I'm going to type in square root 52. And it's going to give me 7.21. I come over here. BD is 7.21. And then the last one, we had square root of 90. Type in 90. I get 9.49. So my calculations I did by hand, leaving them as radicals, is verified through GeoGebra, right? Does that kind of make sense? We can also determine slopes. Okay, I can click on this tool again, go down to the slope option. Okay. Now, when you click on these things, and you don't know maybe the way to use the tool. See how I put my cursor on top of the tool, and it gives me that yellow box, tells me what to choose to run that tool or use that tool. So it just says select a line. Well, come down here, I want to select this line right there, and it's kind of weird where it puts slope. Okay, sometimes, but what they're doing here is that if I had that line, okay, it's just showing you a little excerpt of that line of how rise over run is impacting that line. Does that kind of make sense? Okay, but we see negative 1/3, and that's the value that if we go back here, we found negative 1/3 for C to D, and that's what's showing up. Okay, if I want to do slope again, let's go B to D, and it's showing you this negative 2/3. And then I do this one here, and again, it gives me 0.33 or 1/3. Okay. I don't like how they animate the slope, how they show that, but it does provide you the accurate information. Another way for us to validate and realize that we don't have right angles, not just using slope, but we could come up to the angle tool. All right, now I'm terrible at this, but I should be able to select 3 letters and give me the angle of those 3 letters. But you have to go off of the way that they were created. And I think we created B for, I think these are in order in which you created them. So B came first. I want to go B and then C and D, and I did it wrong. I got that outside angle. So that tells me that I actually need to start at D, go to C, and then go to B. And then I can do the same thing, start at C, go to B, go to D, and then B, D, C. And as I start moving those things around, you see at that angle is 15, that one's 127, that one's 36. So that's verification that we should have marked this thing as simply just scalene, right? So that's what they're trying to get you to do. That's what a coordinate geometry proof. Okay, because we're dealing with coordinates, working in the rectangular coordinate system, the x-y axis, and we're using our distance formulas, sometimes our midpoint formulas, our slope formulas, those types of things, to prove algebraically and geometrically that a shape is, better classified. Instead of just a triangle, we call it a scaling triangle. Instead of just a quadrilateral. Maybe down the road, in the next chapter, we'll call it a parallelogram. Instead of just calling it a parallelogram, maybe we'll still call it a rhombus. It may be better than a rhombus, we can call it a square. And we're going to do these types of things. The number, there's three, I guess, formulas you need to know. Midpoints, we haven't dealt with for a while, but the other two are distance and slope. If you can do distance and slope, pretty much everything that we do coordinate geometry-wise, you're going to be setting yourself up for success. If you can put those in tandem with your geometry rules of, like, how do I declare something that's isosceles, how do I declare something a rhombus, and that kind of stuff. Okay, but the algebra component, those two formulas, you should be okay. Does that help with those two questions at the end from you there, Dave? We're going to continue to see those.